Okay, Unit 6, Forces, Notes page 5. We've done pages 3 and 4 in separate previous videos, so by now we should be pretty fluid with how we run through this. Expect us to do this quickly. One note as a reminder, we already know this, but when you're moving at a constant velocity or at rest, you are in equilibrium. That force 0. Yes, we already know that. There's a reminder. Sometimes you'll see constant speed in a straight line, or they'll show you constant speed with the thing moving straight down a ramp. So those are both also constant velocity. All right, so let's just start hustling. 2 kilogram box. There we go. Mass, 3 kilograms. All right, it's being dragged along a rough surface, so let's just put in what we know. We know the FG, we've done this already. M times G, which comes out to 3 times 9.81, 29.4, let's call it 29 newtons. Fine, got that done. It's being pulled with a horizontal force 50 newtons to the left. Here it is, F external. And for the ink to reload, there it is. See, we even run out of electronic ink. F external, 50 newtons. Let's make this 2 sig figs to the left. It's being dragged along a rough surface, so we know there's friction. We're not sure how much yet. And then it says at a constant speed. So constant speed gives away that this is a net force 0, equilibrium problem. And so our friction is actually going to match our external force, 50 newtons, and our normal force is going to match our weight, 29 newtons. Okay. Don't bother with the fact that this is very strange that the frictional force is bigger than the normal force. Yes, that's not a normal situation. Maybe there's some kind of tacky material between them. Okay, just worry about setting up the diagram. Of course, the acceleration will also come out to 0 meters per second squared. This would be better served with 5 newtons than 5 newtons to make this a little more realistic. All right, let's go down over here. A 12 Newton block is dragged across a rough level surface. So here's a block. They told you it's 12 Newtons, so we already have the FG. Across a rough level surface, so drag, both these words are telling you this friction, by a force of 4 Newton and an angle of 60 degrees above the horizontal. Okay, well, let's pull right. Everybody likes right. So here's 45, 60. So you're being pulled like this way. External force of 4 newtons. This angle is 60 degrees. Make our FG a little bigger so our scale is closer. Okay, the force of friction, well, it's being pulled up and to the right in our picture, so friction will oppose it. Little bitty guy over here. Friction is 1 Newton. All right, cool. So what else can we figure out? Well, there's no spring, so we're not going to worry about that. We already have the friction, no spring. We already have the external, sort of, and we have gravity, we have the weight rather, so we need to figure out the normal force. Now, as we did before, previous page, we have to break that diagonal external force into components. It's up and to the right, so it's how much to the right? Exactly this much. There's your external force in the x direction. And how much up? Exactly this much. Here's your external force in the y direction. We did this on the previous page. That's going to be 4 times the cosine of 60. So 4 cos 60, it's going to be like 3 and change. Let's see what it comes out to. 4 times cosine 60. Oh, sine. I was thinking sine. Sorry. 4 cos 60, that's an easy one. Cos 60 is half, so 4 cos 60 gives you 2 newtons, and then 4 sine 60, which is the one I should have put in here, comes out to 3.46, let's call it 3.5 newtons. Okay, good. And it should be, by the way, just as a gut check, this kind of looks like 45, I should have it tilted more. But 60 degrees is closer to vertical, so you should have a bigger y component than x component. Okay, there it is. So, hash out the diagonal. We don't need that anymore. Look at all this beautiful stuff. All right, now, is the box leaving the ground? Well, no, it's not going to leave the ground. In fact, the ground's still going to push up on it. This is not enough lift force to take it off the ground. So the normal force is actually going to provide the rest of the balance. In the vertical direction, this thing is in equilibrium. It's balanced. You have a normal force. The normal, the balance balancing force is normal plus 3.5 are going to give you 12. What is that? 8.5 Newton normal force. And now we can look at this picture. As is the case with pretty much all of our ground problems, the net force vertically is nothing, but the net force horizontally is something. 2 newtons minus 1 newton, and 1 newton net force. The acceleration then is F net over m. We don't know m yet. M is Fg over g, and roughly speaking, 12 over almost 10 is about 1.2 kilograms. 1.2 kilograms. And so if these are 20s, this is 5/6. 1 over 1.2, which comes out to 0.83 meters per second squared. Good. Okay. Down here, there's a nice one. A moving copper block with a mass of 2 kilograms is decelerating. Okay, let's not get too far ahead of ourselves. Here's a block. Mass, 2 kilograms. What else do we know? The weight, Fg equals mg. So it's about 19.6. Let's just call it 20 newtons. It's moving already, so that's good. They're telling us it's copper, decelerating, friction, steel. Look at all this business. Okay, so copper on steel, oddly particular. We can go and look that business up. We know the acceleration also. One of the nice things about acceleration is, once you know acceleration, you can usually find F net pretty much right away. And in fact, we'll do that here. M times A, which is 2 times 3.53. And so the F net comes out to that 7.06. Let's call it 7.1 newtons negative. Okay, there's your F net. Good. So the copper block, the mass of 2. Now, here are the things to start looking for. What else exists in this problem? Are there any external pull forces? Now it's moving already, decelerating due to friction, so it's sliding along, but is anything pulling it? If they don't tell you there's a pull, there's no pull. That's out. There's no spring. Friction, well, we can choose. Let's say it's moving this way. And friction is going to be this way, although we don't quite know what it is, so we're figuring that out. Is there a normal force? Yes. There's nothing else going on in this picture. The block stays on the ground. The normal will balance the weight. 20 newtons. We did the Fg, so what's left? Well, this is the perfect backwards run on what we've been doing. Hold on! If the F net is negative 7.1, balances vertically, then there must be a net force. There must be a force of 7.1 over here. That force is friction. That force is 7.1 newtons. That's the connection. There's only one force horizontally. That force is the force of friction. All right, pause and we'll go on to the next page.